our entire unit here is to look at the atoms in the periodic table and like how they mix. So we're not doing moles. We're not doing reactions, really. We're just looking at how elements are different from each other. Speaking of elements, what makes one element different from another element? Elements are differentiated by the number of protons in the nucleus. The number of protons. Number of protons. So how many protons something has tells me what element it is. How many protons does hydrogen have? Not all at once. How many protons does hydrogen have? One proton. How many protons does helium have? Two protons. Yes. Lithium has how many protons? 3 protons. So this is the analogy we get to be able to make. If I see an element that has 1 proton, what element is it? It's hydrogen. If I see an element with 2 protons, that element is, it's helium. And rounded out, any element with 3 protons is a lithium. The number of the protons in the nucleus of the atom is known as the atomic number. And it's very simple. The atomic number is how many protons are in the nucleus. That's it. So the big number on the chart, not the big number, the smaller number on the chart, is the atomic number, and that's how many protons are in the nucleus. Okay. A neutral atom. What? No, let's just say it. A neutral atom has no overall charge. So there's no charge, so there's no positives or negatives on a neutral atom. So the number of protons is equal to the number of electrons. So a normal, everyday atom has the same number of protons as electrons because it has an overall charge. All right, we're going to use an example of sodium. I put the little card of sodium right there. It's up on the chart. It's on your page. What's the atomic number of sodium? 11. How many protons does sodium have? 11. What's the charge on a sodium nucleus? Plus 11. Right? It has 11 protons in the nucleus, 11 positive charges. A neutral sodium has how many electrons? 11. Right? It wasn't a very exciting set of blanks, but it's just to show the parity of all the things. The atomic number tells me all these things. The atomic number is 11. It has 11 protons. That means it has a plus 11 charge on the nucleus. And a neutral atom would have 11 electrons. Just got to get all these numbers out. You got to make sure you know all these things. An atom that has gained or lost an electron is called what? So if a sodium doesn't have 11, what's it called? Ion. It's called an ion. Gaining electrons, what kind of charge will you get if you gain electrons? Negative charge. So you get negatively, to spell it in the right grammar, negatively. I think there's an E in here. And losing electrons will get you positive. Positively charged. We have a name for the negatively charged ions. What are they called? No, those are just electrons. What's the ion called when it's negative? Yes, it's called an anion. an anion. And you guys remember the positive one? It's a cation. It's a cation. All right, quick math. Let's figure out the n to the negative 3 ion. How many electrons does it have? First, we got to figure out what element is N. Nitrogen. So, nitrogen. How many electrons does neutral nitrogen have? 7, because it's a number 7. So we'll look, it's number 7. 7 electrons. Did it gain or lose any? Sorry, did it gain or lose? It gained. So, how many? 10 electrons. Right? So, a nitrogen ion, n to the minus 3, is 10 electrons. So that anion has 10 electrons. How many electrons does the SN4 plus ion have? First, we got to figure out what element is Sn. It's tin. So, tin has, what number is tin? Tin is number 50. 50, 5 zeros, 50 electrons. Did it gain or did it lose any? It lost, right? And it lost, how many? Lost 4. Can we do the math on that? 46 electrons. So that's our quick math how to find electrons from ions. Yes, you've done this before. It seems pretty straightforward, right? Nice and easy. Good. So atomic mass, we got to define atomic mass. Both protons and neutrons weigh about 1 gram per mole. So we just add them together. It's the sum of both the protons and the neutrons. So to find number of neutrons, we just subtract. So neutrons. So in case you were wondering, neutrons is a little n with a 0 exponent to show that it has no charge. And that's equal to atomic mass minus atomic number. So, a little neutron sign, just going to write that as a neutron. Neutron. Just to show the symbols still there. So, a neutron is a little n, lowercase n, not a capital N. Capital N is nitrogen. Lowercase n is electron. Oh, sorry, is a neutron. I'll say the right word. Okay. Basically, we can show nuclear arrangement of an atom by writing the mass and the number of certain electrons. So there's a few different ways. There's 3 different ways. We're going to do sodium because I'm not terribly exciting. We're going to do sodium again. So sodium can be written like this. With its mass and its number. So the top number is mass, and the 1 is number on the bottom. So, quick math on sodium. How many neutrons does a sodium have? How many neutrons does a sodium have? No, 12. It's 12. 23 minus 11 is 12. So it's 12. We can also write it this way with just the 23, skipping the 11 part. Why might it be not confusing if I skipped the 11? Basically, all sodiums have to have 11. If it's not 11, it's not sodium. So writing the 11 on the bottom is sometimes unnecessary. So I can also write it sometimes in this way. I can also write Na-23 as a way of showing its mass without getting into exponents. So you'll see this a lot in the textbook because they don't need to break out their exponent button. They can just write Na-23, and that shows me this is a sodium with exactly 23 mass. Now, isotopes exist. Isotopes are atoms with the same number or same element, but with different neutrons. So, changing the number of neutrons in an element doesn't actually change the element at all. The properties of that element are the same, mostly. The chemical reactions are the same. Everything's the same of it. It's just a little heavier. That's all that's different. So, speaking of something that gets quite different when you mess with its mass, we can speak to hydrogen. So, there are 3 different kinds of hydrogen that you can actually get. You can get regular hydrogen, which looks like this. Oops, not like that. Undo. 1,1H. You can get 2,1H and 3,1H. These are all different. So the one on the bottom is because it's hydrogen. Hydrogen has to have 1 proton, but it can have different numbers of neutrons. How many neutrons are in the top one? How many neutrons in regular hydrogen? None, right? 0 neutrons, right? So 0 neutrons. And this is like normal hydrogen. So essentially all hydrogen molecules are this kind. No neutrons, just a proton. That's it. Just straight hydrogen like that. You can make this one. That's 1 neutron. And it actually has a fancy name. It's called deuterium. So it's a pretty fancy word. Deuterium is reasonably common. It's twice as heavy as regular hydrogen. And they use this particular compound in nuclear reactors. Deuterium. 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 So if you make water with this kind of hydrogen instead of regular hydrogen, you get something called heavy water. It's got a mass of 20 instead of 18. So that's actually quite different. Where most of the neutron changes come into like much heavier elements, so it goes from weighing like 114 to 115. It's like that's not that different. But when you go from 1 to 2, that's twice as heavy. You can also get this 2 neutron hydrogen. It's called, let me shuffle that back right over to the right side here. It's called a tritium. And it's radioactive. And radioactive, if you remember your Science 10 at all. You guys remember your Science 10 radioactivity chapter? No. Radioactive just means it will likely decay. It won't hang out in this form a long time. It will decay into something else. The tritium, or 2 neutron hydrogen, tends to come, we can see this as a product of the nuclear fusion in stars. So part of the star fusion reaction has this tritium term in it. So we can find some tritium here on Earth, but it's not much of it. All right, let's see if we can finish up the table giving these symbols. So some of you may have already started this, but let's see if we can go through and figure out the rest of this table. I want you to try it for a second, and I'll stop the record and see if you can do this. All right, that's the chart all filled in, going from all the different pieces, all the correct notation that you've probably seen before, but just now refreshed fully. All right, so this is the next page is the only thing you may not have seen before. So let's look at it. We're looking at the natural mixture of isotopes. So on the periodic table, all the masses listed have decimals in them. Right? Like iron does. Iron is 55.847 grams per mole. Right? It's this ugly number. I think your guys is just rounds to 0.8, but with more significant digits, it's this far. One atom can't have 0.847 protons. That doesn't make any sense. And so this is the average. So this is the average naturally occurring mass. And this is useful because if I have a sample of iron, I can measure out 55 grams, 55.847 grams, and get 1 mole of it. So I don't know that each of the iron atoms have less than 55, and some of the atoms have more than 55. They average out, and we get that here. So what we're going to do is we're going to do a little bit of an example with chlorine. So this experiment with chlorine is shown to have 75% Cl35s and 24% Cl37s. And then we found out that just the 35s have this ridiculously accurate mass, and then just the Cl37s have this unnecessarily accurate mass. I'm not even going to say it out loud. You guys can read. What's the average molar mass of all chlorine atoms in this particular mixture sample? So what we're going to do is we're going to do each percent and add. So we're going to use the mass of the 35. So mass Cl35 is 0.7577. Whenever we see a percent and we're going to do math on it, we always turn that percent into a decimal before doing any math. So now that we've turned the percent into a decimal, we can multiply it by what one of those is going to be. The 35 was 34.96885.2 is a heck of a number, but we're going to do the math. I don't know how they do that, just given in my question. And we're going to do the same thing for the other mass. Mass Cl37, 0.02423 times 36.96593. So many decimals. All right. We're going to multiply these two things and then get those answers. And what we're going to do is we're going to add them together. The first math, adding the masses, I get 26 something. 26, 4, 9, 5, 9. There we go. And this is in grams per mole. I get the other number. It's a lot of numbers. 8, 9, 0.9568 grams per mole. And now what we're going to do is just add them. Add the masses. Sure. Oh. Ah. Is it not 8.9? 0.8. You get an extra 0 in your percent. Oh! I put it there. I put it in the wrong spot. That's what happened. See? I'm writing the wrong thing. That's not how percents work. That's how percents work. 24% is not 0.02. No one told me I was wrong. I can write wrong. Yeah, thankfully, one person told me I was wrong. That's how percents work. Thank you. Let's see what I get. I get 35.4527 grams per mole. I'm using per mole because, like, actually those numbers should be grams per mole in my question here. These numbers should be per mole. I didn't write it carefully enough. Yeah, that's just, those should also be per mole. Mole. That's what they should be. So that was inaccurate for my typing. That's why those are grams per mole, because it is grams per mole. What is the chlorine mass that you have on your table? 35.5. Is that round to the same number? Yes? Yeah, it does. And if you look way over there, you can see that it's even closer to the one on the side. So this is a way to do our natural abundances, or look at what percent the natural abundances are. This is the way they break down. That's it for the lesson today. I do have a good number of practice questions before. The first chunk are all on the protons, neutrons, electrons nonsense, judging by how much you remember that. The last chunk, the 22 to 25, is on this natural abundance check. That's it for me today.